Okay, well, thank you everyone for joining us this afternoon for our webinar. My name is Melissa and I'm with the National Ocean Sciences Bowl. I think I recognize all of your names, so you're probably all associated with the NOSB, but in case you're not, the National Ocean Sciences Bowl is an academic competition for high school students, and the students get tested in their knowledge of everything related to ocean sciences. And each year, to sort of help both with our finals competition and for kids to focus on what they should learn for the competition, we do pick a theme. Given that our finals competition is in Corvallis, Oregon, hosted by Oregon State University this year, we've decided to focus on the theme of blue energy powering the planet with our ocean. As you can probably imagine, the Pacific Northwest coast is actually one of the best sites for harnessing the power of the ocean through this technology, and OSU spends quite a bit of their time, their researchers, looking into both the technologies and possible implementation of such technologies. So that is why we're focusing on that theme for the year. And we do these webinars in part to help prepare the coaches for teaching their teams and possibly their students and other coursework about topics related to the theme. And so this is a webinar that is specifically, organized for coaches, but as you probably know, we do record these webinars, and we hope that you will share them with your teams and other students or other interested educators who you might know. So just to give you a quick rundown of the agenda for this afternoon, we're going to have about a 1-hour presentation from our guest expert, followed by up to 30 minutes of Q&A. So basically, you are all muted right now just so we don't have any background noise interrupting the presentation. So when we get to the Q&A section of the day, or just as you think of questions, feel free to use the little chat box. Just type in your question to me, and at the end, I will read them to our expert so that he may answer your questions. Like I said, we'll try to get through as many questions as we can. Also, if you liked something about today's webinar, make sure you either let me know in that chat box or send an email to nosb@oceanleadership.org. We're always looking for ways to improve what we offer to the coaches, so if you have any ideas, certainly let us know. But then now I'm going to turn it over to our guest expert for the afternoon, Mr. Lesemann. He is with Columbia Power, and today he's going to be talking about his company's efforts to develop a commercial marine renewable energy system. So I'm going to turn it over to him, and he can begin.
Thanks, Melissa. It's a pleasure to be on the webinar with everyone today. As Melissa mentioned, I'm with Columbia Power Technologies, and I will give you some of the perspective today of what it takes to develop wave energy technology, but we'll also talk about marine hydrokinetic energy in general and what is the justification and the push for trying to commercialize the resource. Before we get started, I did want to just take a second and thank all the teachers that are on the call. As the parent of 2 college and 1 high school student, I'm very appreciative of what you do on a day-to-day basis, and very appreciative of the challenges and also the rewards that come along with what you do. So thank you very much. And with that, we'll get started. So for just a quick agenda of what I'd like to cover today, give you a little bit of background on Columbia Power, where we're from, who our partners are, who we develop with, and then step back and take a look at, why do we need marine energy? What role does it fill? What gap does it help fill? And then narrow our focus a little bit and talk about some specific technologies, and then get a little bit deeper with regard to wave energy and some of the trials and tribulations that we and our fellow technology developers go through. And then we'll talk a little bit about our technology development path and what we have, where we are today and what led to that current state. And also we'll finish, obviously, with some Q&A, as Melissa mentioned. So with that, a little bit about Columbia Power Technologies. The company was founded in 2005. We really don't qualify from a timing standpoint as an early stage technology startup, but we are certainly that. The co-founders of Columbia have been heavily involved in renewables 2 wind companies, a number of solar companies, biofuels also. So really a great deal of experience and expertise that led into the formation of Columbia Power. And of all those companies, Columbia is actually the only technology development companies. The rest of the entities that were started were project developers. So they are agnostic to the technology that they need. You know, for a wind project, they may buy turbines from GE or Vestas or Mitsubishi, and their role is to develop the project, to get the wind turbines set up and spinning. We're upstream of that process in trying to develop a technology which we would love to sell to developers or utilities. But a little bit more on that later. So we have deep Oregon State roots, which is part of the reason why I'm speaking with you today. Our engineering team is based in Corvallis, where Oregon State is located. All of our engineers are OSU grads. We've got a great group of people there in Corvallis. And actually being located in Corvallis next to the university with the great facilities that they have, test facilities, and you'll get to see some of those later on in the presentation, it's really assisted us in our technology development path, being able to test our prototypes really in our backyard makes life much quicker and easier for us as we try to iterate towards an optimal design. And we've been very fortunate to receive grant funding from the Department of Energy, from the Department of Navy, from DARPA, the Defense Advanced Research Projects Administration, which is really the forward-looking group for the Department of Defense, and also the Oregon Wave Energy Trust, which is a public-private entity based in Oregon. We have deep relationships with 2 of the national labs, NREL, based in Colorado, and then Sandia, both of which have helped us through our development efforts. And academic partners for us, Oregon State, which is part of the Northwest National Marine Renewable Energy Center, along with the University of Washington, which is also a member of NMREC, but specifically the Applied Physics Lab there at UW. So we have a great team that's been very supportive of us. I haven't shown our industry suppliers, our commercial partners, but we've got a full string of those spread throughout the world, with a heavy concentration on the West Coast, but also in Europe. So a little bit of background on supplying electricity as we get towards where marine hydrokinetics fit into the puzzle here. So what you see in this graph is what a utility would face as it attempts to supply electricity to meet the demand. So this line that you see here is the demand over a day's period. So as people wake up around 6 a.m., electricity demand starts to build, and then as people come home, we still have the air conditioners running in the summer for the most part. 6 p.m., late afternoon, early evening represents the peak, and then from there, as the sun goes down, needs reduce. And so from a utilities perspective, they have to come up with a way to constantly, they cannot not meet this demand. And so how do they do that? Well, they subdivide their, and I'm simplifying here, but because it's a very complex job that they have, but effectively they split their supply into 3 layers. Base load is always on. Base load supplies are meant to run most efficiently when they never get turned off, really except to maintain those units. Intermediate, peaking, so this could be a natural gas combined cycle plant, there are other opportunities there, helps fill the main variability above that base load demand. And then for peaks, which is very expensive power, these types of resources are easy to turn on and off. You can crank them up in a couple minutes and get them running, and then they're quick to be able to be turned off. They are dispatchable, as the utilities would say. And it's the combination of these 3 layers is what allows a utility to meet demand. As you might expect, you have the least expensive on a per kilowatt hour basis at the bottom, and it gets more expensive as you go up. So part of the issue is that we see that renewables are starting to take over. So this is just a very simple graph of global net installations. This is capacity installations in gigawatts, really over a 5-year period from 2010 to 2015. There are a number of reasons why, and this is across the globe. So the reasons change from region to region, from continent to continent. But the trend here is really unmistakable, with wind and solar that are vastly outstripping coal and natural gas. And again, whether a region like Europe, which heavily believes in global warming, or whether it's more cost-based, as it is here in the U.S., driven by some public policy, again, the reasons vary with each region, but the trend is unmistakable. The issue, though, is that we are creating an issue for ourselves, because as you think about nuclear, coal, natural gas, again, whether or not carbon is good or not, that is above and beyond. We could spend a lot of time talking about that. But the issue here is that we are replacing baseload resources. These are resources that have high capacity utilization rates. Sometimes you hear that referred to as capacity factor. You have plants which are running at 90–95% of the year, and we're replacing those with intermittent resources, resources that have lower capacity utilization rates. So renewables, wind and solar are great examples. You know, solar capacity factors, it varies depending on where it's located, but it's usually below 20%. Wind, depending on where it is, can be 25, 30, 35%. Offshore wind can be higher than that. So what's going on as we flip back and think about this graph is we're switching out resources that effectively run all the time with resources that can't run all the time. Now, storage, utility scale energy storage, will help with that. It'll help plane out, it'll help shift that demand, or help shift the supply to meet the demand, if you think back to that peaking curve we looked at a few slides ago. But it's still not going to be enough. And this is where wave energy starts to fit into the picture. So in spite of all of the momentum that wind and solar have, and we're adding billions of dollars of capacity every year, there's still a spot. We have to fill this hole right here that's starting to develop. And we have to have renewables that can run more like base load than like intermittent resources. So one great solution, the solution we love the best, is the ocean. So the ocean is really just a big battery, if you think about it. It's a big battery of stored wind and solar energy. And I'll show you, I'm going to switch to our web page in just a second to give you a more up-to-date view or a real-time view of what the wave regime looks like worldwide. But because the ocean is a big battery, it can deliver energy more consistently. You know, on average, on any beach, roughly 4 million waves come ashore every year. It's that night and day consistency that works in ocean energy's favor, specifically with respect to wave energy. And it's one of the things that, in spite of the difficulty, which again we'll talk about in just a second, of developing a utility scale wave energy technology, it's one of the great appeals. It's what drives everyone, is that ability to supply, the potential to supply such a major part of our electricity demand. I'm going to try to switch here if I can. This is from our website. You know, we welcome everyone to use this as a resource for your teams, for your students. This shows the significant wave height, which is really the average, the 1/3 average wave height that you see that's observed. Significant wave height is actually a methodology that came up during World War II to help standardize visual recording of wave heights and weather conditions. But as you can see, the waves tend to be the strongest where there's a long open fetch of water and a predominant wind blowing across that water. So the West Coast of Europe, West Coast of the U.S., Australia, New Zealand, South Africa, the southern coast of South America. So in the temperate zones, things are obviously more lively than they would be in the tropics along the equator. But those areas that you see red or the darker color is really where the market will end up starting from a wave energy standpoint. And most specifically, it'll be in Western Europe. So for us, while we do the majority of our technology development here in the U.S., the market will start in Western Europe. Renewables have traditionally started in Western Europe, have commercialized there, and then spread back to the U.S., spread worldwide. So onshore wind, solar, offshore wind, again, all getting cranked up in Western Europe before they migrate back. As an example of that, offshore wind in Europe was a $15 billion industry last year. And as many of you know, we just turned on our first wave farm, offshore wind farm in Block Island. So there's Europe is a leader. We don't normally think of it that way, but they are certainly the technology leader when it comes to renewables. So marine energy will help fill the gap. There are a lot of great attributes, as I started to mention, about wave energy. It is the largest untapped resource that we have. It's really close to the demand as most of the population lives very close to the coast. It's energy dense, it's energy rich, it's very consistent, dependable, which again is what appeals to the utilities. At the end of the day, or 2050, there's a very significant amount of potential installed capacity. The DOE estimates, the Department of Energy here in the U.S. estimates that we could supply over 7% of demand with ocean energy. Worldwide, this can go up to 10%. So it can be a very material provider of electricity, provider of supply for the world. So real quick, just a definition here. So marine hydrokinetics, that's the word that we use mainly here in the U.S. to describe marine energy, ocean energy. Sometimes you'll see offshore wind. In fact, I think Dr. Henkel yesterday included offshore wind in her definition of ocean energy. But the differentiation between hydrokinetic, hydrostatic. So on the right, hydrostatic, conventional dams, that's one from California that you see in that picture in the upper right. The lower right is a tidal barrage from France. It is still an impounded water, so it's that static pressure of the tidal flow that helps drive turbines in the bridge that actually you see there. On the hydrokinetic side, we're obviously talking about the creation of energy through the flow of water, whether it's tidal in the upper left, wave, which you see with those red devices, ocean current in the lower left, or river current there in that device in the picture in the lower in the middle. So when I refer to marine energy or ocean energy, I'm broadly speaking about hydrokinetics. The issue is you think about, in spite of that appeal that we talked about there a minute ago of supplying such a material amount of demand worldwide, the ocean is a really tough place to operate, especially if you've got to put a device that's supposed to stay in place for a 20-year service life and consistently and reliably produce electricity. And I try to simplify and boil down the problem of commercializing or developing a commercial wave energy technology through what I call the trilemma here. And the trilemma is three customer requirements, three market requirements that have to be balanced. You can't cheat on one in order to satisfy the other two. And so just real quick what I mean by each of these. So acceptability is environmental acceptability. Can you get the project permitted from the regulators? Do the customers want to buy it? Do the local communities, will they accept the placement of your devices offshore for the circumstance of our devices. And I think you'll hear more about that in the next webinar given by SEARAY. Affordability. We have to have a system. It may not start off affordable, but at the end of the day, it has to meet the local cost requirements. Now, locally in Europe, energy is more expensive than it is in the U.S., which is one of the reasons why markets usually start there in Europe. But if you think about the U.S., Alaska and Hawaii have very different local costs of energy than, say, we do here on the East Coast where I'm located. Areas that burn diesel, for instance, Hawaii is 80% coal and diesel, and most of that's diesel, which you may find hard to believe, but it is. Southeast Alaska, very expensive. They burn quite a bit of diesel fuel there for local supply. They have microgrids. There's really no established utility scale grid. And so you find areas in the U.S. or even customers like the U.S. Navy, which has very expensive electricity. But at the end of the day, to commercialize a system, you have to create something that is locally competitive. You know, in the East Coast, that could be 3-4 cents per kilowatt hour. In other areas of the country, it could be higher, but you certainly need to be locally competitive. And then availability, by that means you have to have a system that's available for 20 years. It needs to have a high capacity factor, which we talked about a minute ago. It needs to be able to be serviced at sea in location. You can't keep dragging a device in and out of the ocean and taking it into port to repair it, because it would create something that's not affordable at the end of the day. So part of the challenge for us as a wave energy technology developer, and the challenge for Tidal and Run-of-River and other developers, is trying to balance these three things. And so a couple examples. So we can't over-engineer a device to make it survivable for 20 years, because then it likely becomes unaffordable. Or we can't come up with a system which the local communities will not accept in order to make it less expensive, because no one will want to buy our equipment. No one will want to develop projects using our equipment. So it's very difficult, and you'll get a flavor for the trilemma as we talk throughout the presentation here. But this is really the core of the challenge of what we try to conquer on a day-to-day basis. So again, some of the important considerations here that we have to think about as we maybe dive at a little bit deeper level than the trilemma, you know, performance, efficiency, and cost. So we have to capture the mechanical energy from every wave, and then we have to convert that into electrical energy. And so we're looking for the most efficient, cost-effective capture conversion chain that we can come up with. Some of our competitors have multiple conversion cycles. They'll capture the mechanical energy. They'll store it in a hydraulic, store that energy through pressurized hydraulics, and then they'll spin a turbine maybe onshore or on the device. We tend to do things a little bit differently. We have a single capture conversion cycle because we think that's the most efficient way to go. But again, at the end of the day, it's all about cost. Some of the impacts in the device survivability, we've talked about that. Some of the other things that we need to think about are how easy is something to manufacture? How easy is it to deploy? You know, our systems are very large. I mean, they're 25 meters in each direction. When they're fully ballasted, they can weigh well over 1,000 tons. And so that's, you're really talking about dragging a ship around and deploying a ship out in the ocean, or an array of ships. And so for us, we have to think about how easy is it to deploy? Can we just pull it with a tugboat, or do we need specialized equipment in order to get that equipment installed and in the water? And then how easy is it to maintain? Again, if we have to pull something in to port every time it breaks, it's really not going to be cost effective at the end of the day, and so we've started to violate the trilemma. And then some of the other considerations are, where do you want to locate the device? We've chosen to put our system offshore. Others want to be closer to the beach, closer to the shore, or even onshore, and we'll see some examples of that in just a minute. And then where do you want to be in the water column? Floating is where we are, so we're an offshore floating system. We like being in deeper water, you know, over 60, 70, 80 meters worth of depth. It's really out of sight, out of mind for the local stakeholders. Tends to be out of the way of local uses. But other folks want to be bottom mounted. They feel like being out of the destructive waves at the surface makes an easier, cheaper device. But then you run into issues again on how do you get a hold of a device quickly and easily that's got to be bottom mounted, whether it's in the surf zone or whether it's in deeper water, 20, 25 meters of water. Each decision that you make comes with its own set of challenges. So here are some of the device types, and again, I think Dr. Hinkle may have talked about some of this yesterday, but just a quick review, and I'll talk a little bit about some of the pros and cons of each of these. And Aquarette, so if any of you are looking for resources, all of these gifts are available, plus some other great resources, teaching resources, posters, and so forth, at aquarette.com. It's a European-funded entity, and they've done a great job with some teaching tools. So attenuators in the upper left there, attenuators are really good at energy capture. They're very efficient, but they tend not to be very survivable. As you imagine that joint there in the middle of those two flaps that are moving up and down, that joint is a really tough area to make survivable if you think of a really, really large wave coming through. And we need to design our systems to plan for the 50 or 100-year storm. So that once every century storm and the wave heights that are going to come along with that, we have to design for that. And so the attenuators tend to be a little weak on the survivability side, even though they're really good on the energy capture side. So moving across the top, oscillating wave surge. These are flaps, sort of like a book cover that gets pushed with the waves. These tend to be near shore, almost in the surf zone, usually in 15, 20 meters worth of water. They can be made highly survivable, but very difficult to maintain. Also difficult to deploy. It tends to be a very rough area. Overtopping systems, these can be onshore or in deeper water. Water flows over the top and then flows through some sort of exit and tends to spin a turbine as it exits the top zone there. Point absorbers in the lower left. These are really highly survivable devices. They can be bottom mounted, as you see here. They can also be floating. We started off as a floating point absorber. Our device now is actually a hybrid of a point absorber and an attenuator. We like to think that we've combined the best of both worlds, the survivability of a point absorber with the energy capture benefits of an attenuator. Pressure differential systems. As a wave rolls by, the trough of the wave creates pressure that can either push air through a turbine. There are a number of different methodologies that people use there. And as the peak comes through, that pressure is relieved and the air will spin back in the other direction. Similar type of mechanism of action for oscillating water columns. Oscillating water columns can also be onshore or floating deeper water. Again, as the peak of a wave rolls through the oscillating water column, it pressurizes air in that plenum. That air then is pushed through an exit port and spins a turbine or an air fan. As the trough of the wave comes through, it creates a vacuum. Usually those blades will flip in the other direction and will start to spin in the other direction as the air is sucked back through as created by that vacuum. So just some specific examples. I've shown graphics here rather than pictures, just so you can get a fuller view of what the devices look like. And again, I think Dr. Hinkle may have done a similar situation. So attenuator long, almost like sausage link type systems. So really good at energy capture, but again with some survivability issues. That's actually a picture of a Scottish company. You'll see that this is worldwide here. Oscillating surge. This is a picture of a Finnish company's oscillating wave surge device, AW Energy. Overtopping, that system's called the Wave Dragon. A linear point absorber here, that's a floating system. It may not quite look like it in that graphic, but that floats and moves up and down in a linear fashion. Pressure differential M3, which is another Oregon company. You see one of the renditions of their device, and then an Australian company with oscillating water column. And you can see the large fan there. So each of our competitors really has chosen a variety of potential development paths. The early generation of technology developers, specifically Polamis, that attenuator developer, and the oscillating water column developer that you saw on the previous screen, they made a choice to focus on device scale first. So I want to try to get a really large piece of equipment in the water as quickly as possible. And once I figure out how to make a device that is survivable, then I'll worry about making something that's economic at the end of the day. Part of the issue of doing this, focusing on device scale first, doing some really large deployments, is it's a really expensive way to innovate. And the problem is that you tend to literally and figuratively sort of design yourself into a corner here. And there hasn't been a lot of success in going out along the x-axis and then trying to turn north, to turn up, to make a practical device into an economic and practical device. Many of you may be familiar with the Wave Energy Prize, which is a competition that the DOE just ran. And there was an Oregon company that was very successful there. So again, some more Oregon roots. They won the Wave Energy Prize, which is similar to the X Prize on the rocket side. But the Wave Energy Prize was meant to come up with an alternative development path. And that alternative development path says there is a less expensive way to potentially figure your way through the commercialization of a device. And so the Wave Energy Prize says we're going to try to head up and make a really economical device. What are the most efficient devices from an energy capture standpoint? And once we figure out what's best from an energy capture standpoint, we will build up scale and try to make it most productive. Because again, this is where you want, this is the goal. This is a practical, economic device. From a potential customer's point of view, this is a device that not only the manufacturer can make, but that I want to buy. Thinking back to the trilemma, it's an affordable, acceptable, available device. At Columbia, we've taken a little bit of a different path. We've tried to be a little more holistic in our view and taking into account really sort of both sides of the equation. So we've developed more, and you'll see this in some of the pictures that I'll show you, we've developed more in this sort of flat spiral. So we put a larger device in the water, we'll learn about that larger device, we'll learn about how to make it more economic. Maybe we have to back up and go to smaller scale as we make some of those fixes and we get rid of the fatal flaws in the technology. And this path takes a little bit longer, but we'd like to say it ends up being the most cost efficient at the end of the day, the most time efficient at the end of the day, and get you to the upper right quadrant really as quickly and as efficiently as possible. So this is our solution. We call it the STINGRAY. Within the STINGRAY, you have two floats, a forward float and an aft float. Those two floats move independently of each other. They move independently of the nacelle that you see here. The nacelle is that central cylinder. The nacelle contains two direct drive permanent magnet generators. This is the same type of generator that you would see in an offshore wind turbine It's actually the type of technology that dominates. Really 85% of offshore wind installations in Europe are direct drive permanent magnet generators. And we can talk a little bit about more of that if anyone has a question about that. But each of these floats turns its own generator inside the nacelle. So the waves for us would be coming in this direction. Again, this is a very large device, almost 25 meters in every direction, well over 1,000 tons when it's fully ballasted. I'll show you some additional pictures in just a second. But as each float moves up and down, it oscillates the generator that it drives backwards and forwards. So we don't spin in a continuous direction like an offshore wind turbine or a wind turbine would spin in a clockwise direction. Our generator oscillates back and forth. But the main body, the nacelle and these spars, this square here, that's also moving in the water. And so as it moves, it's really the relative motion between the nacelle and each of the individual floats is how we make electricity. We're trying to accentuate the relative movement between each of those bodies as much as possible. The more relative movement that we create, the more electricity that we generate. So this is an example, very simplified deployment of a STINGRAY in the water. We have a very simple mooring system. If you were going to moor a boat over the winter, you'd have a bow line and a stern line, no different for us. An array, a project would be an array of these devices, so you would see maybe 10 per square mile in the ocean, all set up in a matrix, each interconnected. The electricity flows out of the device into this collection point and then moves ashore to the grid interconnect. The power that we produce has to be conditioned. For the early systems, we are producing DC power that gets conditioned to grid-compatible AC power. So you have AC flowing out of each of the devices for the grid interconnect. As arrays get larger and larger, you'll see DC gets shipped ashore, and the conditioning happen on shore right for the grid interconnect. This allows for a more cost-effective installation because we don't have to put the conditioning equipment, the electric plant, on each of the devices. We have a very simple mooring system, as I mentioned. It's a reduced footprint. As a number of other wave energy devices will have multiple mooring lines, which creates an issue potentially for migratory mammals. I know Dr. Hinkle talked about this yesterday. So for us, the less gear that we have in the water, the more acceptable our devices are to the local users, to the crabbers, to the fishermen, to the local communities. Again, thinking about the trilemma, we've got to create a device, again, that's acceptable to everyone and for the environment as much as making it affordable. So a quick animation here of our latest version, the STINGRAY version 3.2. For those of you that are interested, this modeling was done in ANSYS Aqua software program. We'll go subsurface here in just a second. You can see each of the floats will move independently of the nacelle. The nacelle is also moving. So again, we're just trying to accentuate the relative movement between each. You can see the mooring line coming out of the right side. Again, the waves coming from your right to left. And then the umbilical, which is carrying the electricity of the device, is that line that's hanging down. Our system likes to stay aligned in the predominant wave direction. It's one of the reasons why we don't need all those additional mooring lines. It's one of the lessons that we learned with one of our deployments in Puget Sound, that if you have 3 lines connecting the device, only one of the lines is holding all the load at any one time. And so you might as well make that one line handle all of the load and have redundancy built in rather than putting all that extra gear in the water, cost and environmental all figuring in there. So how did we get to the STINGRAY? So just a real quick history and some of the evolution of our design. This system here, which was a linear point absorber, was what we originally licensed from Oregon State. This was actually a undergraduate project of one of our engineers. We took that design and actually we did a sea trial with that L1 design. The L10 was an enhancement of that system. In the L10, what you see, if that's the water line, the device is moving up and down through that float. This was a composite, a fiberglass hull structure, again using a permanent magnet generator. We came to the conclusion after testing this device that we needed to come up with something that was more cost effective at the end of the day, that captured more energy. And this is where we made that leap from a point absorber to a hybrid device, the combination point absorber and attenuator. One of the issues with the linear point absorber is that you have wasted capital investment. Because of the nature of that device, really only 1/3 of your generator is active at any one time. If you think about a generator, a linear generator, if that is the rotor, the magnet, so to speak, and you have the copper coils wound around that rotor. Sorry, I'm not a very good artist. But as that rotor goes up and down, a lot of the 2/3 of the rotor is never really covered by a copper coil, and so you're not generating electricity. So part of the first aha for us was this shift from a linear device to a rotary device. And we took that linear generator and we turned it into a circle. So if that's the rotor, and this is the stator, whereas this is the copper coils before, we have 100% utilization. So all of the investment that we've made in that generator is now active at any one point. We were also able to add a second generator to design, again, taking advantage of the capital investment in that whole structure, and by adding a second generator, making it that much more productive. So with the MANTARAY, 2 wings, and I'm going to show some clips of some of the tests that we did with each of these devices in just a second. The MANTARAY, we moved to a 2-wing. Those were 2 symmetrical floats, a very small cubicle in the cell. One of the things that we learned as we were testing the MANTARAY, that if we made the nacelle larger, that we captured more energy. So as we move from the MANTA to the SEARAY, you can see the nacelle here is a larger cylinder. It's a larger part of the overall device. We capture more energy that way. One of the things that we learned with the SEARAY is that, I'm going to erase these real quick. One of the things that we learned with the SEARAY is that the floats, you see these little pieces here, those end stops were meant to keep the floats from banging into each other. It worked great, except for we were banging those end stops too hard. And as we try to scale that device up to a utility scale system, the engineering and the capital investment around trying to keep those floats from banging into each other was just going to be, it was going to be way too expensive. So again, I keep beating the dead horse here, but we were going to start to violate the affordability side of the trilemma. We make an investment in the engineering and the capital costs of the structure, but that's too much and the device becomes too expensive. So another big aha, and again it sort of seems very obvious at this point, but another big aha for us was we shifted the aft float back in the STINGRAY design, and I will show you this here. Let me get rid of these annotations. So we shifted this aft float back, and so now in a really heavy sea, this forward float will just roll over and it nests inside of the aft float. The device is still working. It's still making electricity. It's not as efficient as it would be with the float in its nominal forward-facing position, but the device passively protects itself. It's a very survivable design, and we actually found that power production went up when we made this change. So this is an example of trying to create something that is more available, more cost-effective, and more affordable at the end of the day. This is a very busy slide, sorry for that, but just to give you a sort of a feel where we've been through and give you some context as we look at some of the clips of the testing that we've done. These are all, except for the Puget Sound, except for this test here, these are all in facilities at Oregon State. At the NIMREC test facilities, there's both a long wave flume, which this test was done in, and then there's the tsunami wave basin, which this test, and this test were all done in. All these projects sponsored by either the Navy or the Department of Energy. Both of those groups, both of those federal partners have been critical to our ability to sort of rapidly innovate our way through. As you can see, while we've been around for a while, over this 3-year span, we made some very significant innovation in our efforts to commercialize a system. So this is the MANTARAY in the wave flume at Oregon State. You can see the two floats moving independently of each other in this clip. These are some really large relative waves. I'll run that again here. Hopefully, maybe not. So at scale, that's a 1/15th scale unit. Those waves were probably 70 to 80 feet at full scale. This was, again, part of our effort to make sure we have a survivable system as we're designing towards the 50, 100-year storm. As we made the move towards the SEARAY, this is one of the early modeling efforts that we made with the SEARAY. This is, again, in Aqua. This is a December storm off the Oregon coast is what we're emulating here. And again, you can see the two floats moving independently of each other, and the cell, which is significantly larger here in this shape than what we had before. This is the Puget Sound test that we did. For those of you familiar with the Seattle area, that's Discovery Park there in the background. This unit was in the water for 13 months. Was a great test for us. We learned a tremendous amount. You can see the end stops there, the red rubber pieces, and in a really violent storm, the collisions were very significant, really too significant, which is why we ended up moving the aft float back. Here in Puget Sound, even though you would consider this to be a relatively calm place, during winter storms, we saw 10-foot waves. This is a 1/7 scale device, so at full scale we were seeing 70-foot waves at this spot. And we picked this spot because with the shape of Puget Sound and the storms during the winter, you have a long open fetch of water stretching down towards Tacoma. The storms tend to come straight up the sound, and so over that 20-mile fetch, and with the storms that you get there locally, it was able to generate some very large local waves. So this was a great test for us, proved our survivability of the design, but also made us understand that we needed to continue to work on the economics of the device. This is a test. So here's a perfect example of having to back up and scale. When we moved the aft float back, we needed to really back up and went from a 1/7 scale device to a 33rd scale device. So move back. So the SEARAY here was 7th scale. This is 33rd. This is back at Oregon State in the tsunami wave basin where we had done significant testing otherwise. We're doing motion tracking on the device. You can see the LED pulls there as we're capturing that. These tests for us span over a 3-week basis usually. Again, it's one of the great things of being there in Corvallis is our engineers get to go home at night and we can do 3 weeks of very intensive testing. One of the tests that we are involved in now is a DOE-sponsored test. This is at the National Wind Technology Center. Again, our generator, our internals are very similar to what you would see in a wind turbine. One of the facilities that they have, and this is located in Boulder, Colorado, is this 5-megawatt dynamometer. Normally you would see a wind turbine nacelle hooked on to the dynamometer. The dynamometer is this piece of equipment here. We're able to exert non-torque loads on the device. But this dynamometer is also smart enough where we can feed real seas data into it. So it will oscillate the generator back and forth. This generator here that you see is really just sort of half of the equipment. This is the rotor. The magnets for the rotor will fit along these tracks that you see. What you don't see here is the outer housing. That outer housing will fit over the entire circumference of the device. This is the largest direct drive permanent magnet generator that we know of on record. That's part of what we're testing here is the mechanical design. A very large manufacturer whose names you would all recognize provided both the power electronics and the active materials for the generator. This is a little over 6.5 meter diameter generator. Over that entire circumference, we are maintaining a 4 millimeter air gap between the rotors and the stators. And again, that design is proprietary to us, but it is that mechanical design that is novel to the world and is what we are validating here in this test. So one last thing that I wanted to show is a low power system, and I'm actually going to stop this and then I'll restart it. Our main focus is utility scale market, so selling our equipment to utilities, developing large scale wave energy projects. A byproduct of that research is low power systems. So as you see the system here, you will recognize really the DNA of that system is coming from our two-float design. But this low-power application, this one was designed for DARPA. It's meant to run a low-power, think in the watts rather than megawatts range, run a deep-sea sensor. It is meant to be independent. It's not grid-connected. You could use these devices for harbor security. You could use them for oceanographic research. You could use them for defense purposes, for monitoring what's going on in the deeper ocean where it's not cost effective. And the appeal of a wave energy device is that you break the cycle of having to recover devices, replace the batteries, redeploy. So our system is meant to keep the battery topped off and is hopefully allows it to be deployed longer, have greater mission persistence, and a lower overall cost of ownership. So I'm going to turn on the sound here and start this over.
A new source of power at sea. Capturing the energy of ocean waves and using that energy to generate electricity. And the whole idea here is to take a completely different approach to generating energy in the ocean. An idea that evolved quickly at the University of Washington's Applied Physics Laboratory, in collaboration with Columbia Power Technologies and the Monterey Bay Aquarium Research Institute. Just a year ago, we had a concept, some sketches on the whiteboard. We didn't know quite what this thing was going to look like. This thing is called WEBS, the Wave Energy Buoy that self-deploys. What it does is serve as a source of electrical power at sea. As opposed to typical wave energy conversion devices, which are anchored to the seafloor and generate large amounts of power for sustaining onshore needs, this is all about having energy available in an offshore environment. There's no anchor. It's a free drifting system.
Okay, so this device here is a 1/7 scale model of WEBS. We have the surface expression up top here that has two floats essential in the cell that actually has the power generating equipment inside it, and it's connected by a tether down here to a heave plate that's about 60 meters down the water column.
And University of Washington mechanical engineering student Curtis Roosh came aboard the WEBS project early to develop a model.
Paul sent along his drawings of a SolidWorks model of what the whole device would look like, and a bunch of preliminary specs for what the different spring forces would look like in the device, and all the lengths and weights, and an idea of buoyancy. And I was able to take all that and put it into the model and start running it at various wave conditions just to see if we were capturing a motion that looked reasonable.
So with that, Melissa, I'm done, and hope everyone found that informative, and love to take any questions that people have.
Sure. Well, again, thank you very much, Reenst, for the presentation. I know we have one question that came in kind of early in the presentation, but yeah, here's your chance to type in your questions. That's one of the main reasons for participating live versus watching the recording, is that you get to ask your specific questions. The one question that came in, and I kind of expect there might be a question along this line, is asking, do you expect the Department of Energy grants to continue under the Trump administration, which has been a vocal supporter of coal energy?
That's a great question. I wish I knew the answer to that. I think that one of the great things about wave energy is that it has a number of, and ocean energy in general, I should say, marine hydrokinetics, is that it's more than just a new energy source. There's also economic development that it generates. You know, these devices need to, they're very large, they need to be made and built in coastal communities. You can help revitalize shipbuilding. As people transition away from fishing and crabbing, there's an ability to redeploy those fleets, redeploy the labor, and provide significant jobs. So I would, obviously we hope yes. It remains to be seen where the Department of Energy budget ends up at the end of the day as we push forward. But we're certainly hopeful that folks in Washington will appreciate the benefits, both from an economic development standpoint, but also bringing a new energy resource to bear.
Okay. Yeah, feel free to type in your questions. I know I have one. So I was actually lucky enough to go see when they actually gave out the Wave Energy Prize back in November. And so I got to see a couple of the people who were up for the prize and talk to them. And the one thing that they mentioned was the cost of testing the equipment. Could you maybe speak a little bit about that? It was almost equivalent or greater than the cost of ship time. So just the testing of your smaller models, how much does that typically cost?
Sure. In fact, I'll just sort of work my way backwards in the presentation here and give you some idea of the cost of these tests overall. So this, let me turn off the sound here. So this test was approximately, this was somewhat over $1 million for all of the development and manufacturing and build of this low power system. This generator test will end up being over a $5 million project, and these are jointly sponsored by ourselves and by the federal partner. This test was significantly less expensive. It's one of the great things about being in the tank. This is approximately a $300,000 test. This was almost exactly a $2 million project all in. This was a $750,000 project, I believe. So yes, you can see that there are some very significant costs that are associated with testing these systems.
Okay, someone had a question, probably talking about the pieces of equipment that you're specifically working with. Are there any significant concerns regarding harm to marine mammals or other sea life?
Yes, it's one of the things that we really have to focus on. I mentioned mammal migration. if you think about from a whale's perspective, a wave energy project, an array of devices, all those mooring lines, the devices can really almost look like a fence in the water if you have too much gear. And so one of the things that's incumbent upon us is coming up with ways to avoid creating that appearance of a fence. One of the questions I think is that Sarah and her colleagues have to help us answer is, do we want to try to divert mammals from migrating through the project, or do we want to sort of create avenues for them to come through? We need to think about the effects of putting our anchors on the bottom. Are we creating habitat where habitat didn't exist before? We have to watch out and obviously not build in marine preserves. But then again, we can also help to build habitats. We build habitats all the time by sinking vessels and putting other structures on the seafloor. Our systems can provide, initial habitat, or it can help spark habitat. We need to think about commercial uses, so we can't be in navigation channels. When we were in Puget Sound, we were right on the navigation channel heading into Seattle, and we're actually run over. Everything was fine, but we were run over by a boat that had strayed too far to the edge of the navigation channel. So there are lots of different perspectives in marine spatial planning, both from an environmental standpoint, but also a commercial use standpoint. It certainly makes life complicated, but it's certainly something that we have to think about also.
Okay, along the lines of what you were just saying about being run over by the boat, someone asked if you put 10 stingrays at industrial scale in a square mile with all the mooring and power lines, does that make the whole area a danger either to boating or shipping?
Yes, it would be there won't be any navigation allowed. The Coast Guard, who is responsible for this, the Coast Guard really helps with, or is, for Puget Sound, they were a critical or a key part of the planning, marine spatial planning for that. The Coast Guard, they will mark off a project as a no navigation zone. So if you pulled out a chart right now off the Danish coast, you will see that significant areas are marked off for offshore wind farms. So yes, you will not be able to navigate through from a commercial standpoint.
Okay. Are there any operational wave energy generators in the U.S. at any scale? If not, where do you think the first will be located and why?
Yes, so there are active devices in Hawaii right now. Really, the industry is going through various stages of research and development. We are on the pre-commercial validation side. You see that large generator that we're testing in Colorado. The Wave Energy Prize companies are all really just getting started off with smaller, early, small-scale devices. But in the U.S. right now operating, the U.S. Navy has created a grid-connected test berth off of the Oahu coast. So those of you familiar with Oahu, there's a Marine Corps base at Kaneohe Bay. The Navy has had a shallow water test berth in 20 meters, 25 meters of water, maybe 30, for quite a while. They just extended that berth. They extended the grid connection into a 60 and 80 meter berth. We'll actually be going into the 80 meter berth next year with a Stingray. But right now there is a device in the 30 meter berth, another Oregon company called NWEI, and then a Norwegian company called Fred Olsen has a device in the 60 meter berth. There are sort of constantly devices coming and going in testing. In Europe, there are a number of devices being tested at grid-connected test centers there. So no commercial projects. I should also mention Australia. There are a number of very large-scale projects going on in Australia. And I would say that Western Europe, the U.S., Australia are really, and now China, which is quickly catching up, are all really the centers of wave energy and tidal energy R&D.
How close do you believe you are with the STINGRAY to a commercial model that could be used successfully on a larger scale, and what major hurdles do you have yet to overcome?
Yeah, these are all great questions. So we would like to believe that the STINGRAY that we will put in the water in Hawaii, which will be a large-scale device, that's the final validation that we need before moving to commercialization. It will remain to be seen where those first early commercial projects will be developed. Would it be Hawaii, which has a very high cost of energy? I think the cost of energy, in Hawaii is roughly 35 cents per kilowatt hour. On the mainland, we pay, somewhere 8, 9, 10, 11, 12 cents per kilowatt hour. So that's a prime spot for those early commercial developments. So whether it's there or Southeast Alaska or off the Pacific West Coast or the West Coast of Europe, we'd like to think that the next device after Hawaii will be that first commercial deployment. What do we have to do to get to that point? So we have to finish that generator test that I showed you the picture of in California. We need to validate that our mechanical design for that large-scale generator operates as we say that it will. Then we have to make sure that we've got all the funding that we need to build that large-scale device in Hawaii. We have design work and some engineering work. We've got a number of projects going on right now to optimize the structure for the Hawaiian device, to come up with ways to make the installation and operations and maintenance of that device less expensive. We have to make sure that we understand the logistics of building the device on the west coast of the U.S. and then getting it to Hawaii. Hawaii is a long way away, so that's a very long tow. Do we build the pieces that can be easily assembled, like Tinker Toys, so to speak, in Hawaii, or do we build the whole device on the west coast and then ship it whole to Hawaii? So we've got a number of engineering, logistics, capital, all sorts of decisions that we need to make and hurdles that we need to overcome. And then as we move past the Hawaiian device and we get that device successfully deployed, and one of the steps there that we have to do is we have to have that device certified. We've already been through a first stage certification, and that certification is a third-party independent review of our system to make sure it's seaworthy. If you were going to build a ship and then launch that ship, in order to get insured, you have to be certified, so we have to go through a very similar process, but one that's specifically geared towards wave energy devices. But to get in the water in Hawaii, we have to get our certification up to date. And then, as we move towards that first commercial deployment, we need to find a customer, whether that would be a domestic or an international customer. We have to find a site. We would likely want to pick one of the pre-existing test centers because they're already pre-permitted. The grid infrastructure is already there. The mooring systems are already there. The local communities are already accustomed to the devices. So in order to accelerate the timeline, we would probably pick one of those pre-existing test centers. But as you can imagine, we've got a lot of work to do in order to get that first commercial device in the water.
Yeah, and I think this next question is kind of in tune with that. Since you have all these challenges, they're asking, where do you see the opportunities and needs, basically in terms of, oceanographers, physics, electrical engineers, mechanical engineers? Since we're dealing with high school students, where are the needs and opportunities for them in the future?
It is all of the above. So we need electrical engineers, we need mechanical engineers, we need hydrodynamicists, we need software engineers, we need folks that are technically oriented from a manufacturing and fabrication standpoint. As everyone can probably understand, I'm not an engineer or a researcher based on the presentation that you just saw, but they are our lifeblood. And it's one of the reasons why we love being in Corvallis, is you have such a great pipeline of engineers and technically oriented folks coming out of Oregon State. And it's why we've partnered with both Oregon State and University of Washington, is that talent. So I think that's one of the great things that I would love to come out of this presentation, is as an appreciation for the technical skills, the engineering skills that we need in order to be successful, because we are nowhere without the engineers and the modelers that have gotten us this far. In fact, in Columbia, I'm the only non-technical person in the entire company.
Okay. All right. So I think this is a good topic to sort of get kids interested and excited. And through NOSB, we're also always trying to tell kids that there's way more opportunities out there for them to get jobs. And I think this is a really good way to highlight that you can have all these different skills and maybe not want to work specifically out on the ocean, but be able to work in jobs that are related to the ocean. So I appreciate those answers. Thank you. Did we have any other questions? Okay, so I'd like to thank you all for participating today, and I'd like to say thank you again to Reenst for presenting today. I think this was an interesting introduction to sort of another side of marine renewable energy, thinking it sort of more from a corporation side, but he definitely hit on everything that's necessary for getting these pieces of equipment and technologies both tested and potentially operational. So thank you again for presenting and being part of our webinar series.
My pleasure.
And just to let everyone know, we do have one more presentation coming up on Thursday. It's going to be at 7 p.m. Eastern, and it's Katie Jacobson, and she's with Oregon Sea Grant, and she's sort of going to be talking about all the different stakeholders that are involved. So both of our past two presenters have sort of touched on this, but it's more than just the researchers and the technology companies. So hers is sort of more the social science side of marine renewable energy. So we hope that you will be able to join us for that as well. And we are recording these, as I said. I will have this recording up on our YouTube station tomorrow morning, and the link to it will be on our website. So I hope that you will certainly share this recording with your students and other educators, and feel free to share them as broadly as possible. Part of the reason we record them is we want them to be a fantastic resource for both educators and their students. So thanks again. Oh, and I will make one final comment. Some of the tanks that you saw in Brent's presentation, the students who do come to finals this year will get to see those. They will get to see those facilities. That's one of the activities we're going to have for the teams who get knocked out of competition. So maybe this will be a little more emphasis for your teams to prepare for their regional competitions if they think they can go see this firsthand for themselves. So thanks again for everyone for participating, and we hope that we will have you joining us on Thursday night as well. Thanks again, Reenst.
Thank you.
Okay, well,